Okay, so this is problem number 5, chapter 2. And it's a question about a boat race. So let's go ahead and make up a lake. So here's our lake. They're having 2 boats. They're going to travel across this lake. And the distance across the lake is 60 kilometers. So put a double arrow here. So this is 60 kilometers. And one boat goes 60 kilometers per hour and returns at 60 kilometers per hour. That's boat A. Boat B goes across at 30 kilometers per hour and then realizes they're going too slow once they get to the other side, which they should have figured out a lot earlier than that. And so then they return at 90 kilometers per hour. So the question is, how long does it, which boat wins? And what is the average velocity of the winning boat? So the one that wins is the one that takes the least amount of time to go from here to here and then back again. So if we look at boat A, how do we figure that out? Well, we use the definition of velocity. Velocity is equal to the change in displacement given the change in time. So we're going to look at 2 separate parts. We're going to look at the change from here to here, and then as we go back the other direction. And really what we're looking at is we're looking at speed. As we'll see why that is true later. Speed is just the magnitude of the velocity. So if you take the magnitude, a lot of times in math you use this double vertical lines to show magnitude. Okay. And the velocity is equal to the speed if you're going, say, from left to right. If we define left to right as positive x. So the speed is positive. Whether we go this direction or that direction, the velocity is positive in this direction. But if we go in the other direction, the velocity is negative. So find a little point there. So really all we have to do is we just have to reconfigure this equation to find out time. So the amount of time, delta t, is equal to the change in displacement divided by the velocity. So we're going to, let's call this 1, this is point 1, this is point 2. So if we're going from 1 to 2, what happens? Well, for boat A, the speed, we call it speed or velocity at this particular point there, just as it goes across. So we're going to call it, let's use the velocity right now. So the time is the distance, delta x, which is 60 kilometers. And we divide by the speed, which is 60 kilometers per hour. And so 60 divided by 60 is 1. And the kilometers cancel out, and the hours comes up to the top. So the time to go from point 1 to point 2 is 1 hour. And then if we go the opposite direction, because we're going the same speed, in this case 60 kilometers per hour, so we take 60 kilometers and we divide by 60 kilometers per hour. And in a strict sense, we're dealing with velocity. This would be negative, and this would also be negative because we would be going from right to left. So let's just do that. So the amount of time it takes, time is always positive. We usually start at time t equals 0, and then we go positive. So anyway, as you can see, the second amount of time is also 1 hour. So the total time for boat A to travel across the lake and back again is 2 hours. So now let's look at boat B. So the same thing, if you look at the going from 1 to 2, the time is the velocity, which is 30 kilometers. Actually, the distance is 60 kilometers there. We're dividing by the distance is 60 kilometers. We divide by 30 kilometers per hour. And so 60 divided by 30 is 2 hours. So that's how long it takes for them to go across the lake from left to right. Well, if we look down here, it took 2 hours for the other boat to go all the way one direction and back again. So at this point, we can say, well, obviously boat A wins. But let's just see how much longer it takes, how far behind they are. So if you look at the amount of time, you have, again, 60 kilometers going negative because it's in the negative x direction. And we divide by negative 90 kilometers per hour. Again, it's because we're going from right to left, it's negative. So delta t is going to be 60 divided by 90 is 2/3. 2/3 of an hour is 40 minutes. So you can say 2/3 of an hour, which is 40 minutes. And so the second boat will arrive 40 minutes later than the first boat, because the total time for boat B is 2 hours, which is the time it took to go from one side to the other, plus 40 minutes, which is the time it took to go back. And so that's 2 hours, 40 minutes. As I said, if they could actually see, which they probably can't, but they probably have somebody in the radio saying, hey, you guys already lost because you're not even close. But anyway, so the first boat A wins by 40 minutes. That's part A. And the question, what is the average velocity of the winning boat? Boat A. Well, what is a velocity? Velocity is equal to the change in displacement divided by the change in time. So the time for boat A is 2 hours. It took 2 hours to go from the left-hand side of the lake to the right-hand side of the lake and back again. But let's just put x equals 0 here. So we go out here. After 1 hour, we're at x equals 60 kilometers. And then we go back. And we get back. So that's negative 60. So we go plus 60, minus 60. We end up back at the starting point. So as far as the velocity is concerned, the velocity is a change in displacement. Well, the actual change in displacement is 0, because we go here and we come back and we're in that where we started. So delta x is 0. The time is 2 hours. 0 divided by 2. This is kilometers. So we end up at 0 kilometers per hour. So that's the average velocity. Now, if we were to do the speed would be the distance traveled, not the net displacement. So we travel 60 kilometers this direction. We travel another 60 kilometers. So we'd have 120 kilometers. We divide by 2 hours. And so 120 divided by 2 is 60 kilometers per hour, which is not a surprise because that's what the problem said, is we went 60 kilometers an hour this direction, and then we went back again. So that's our average speed, is 60 kilometers per hour. Our average velocity for the total trip is actually 0.
Recording started.
Okay, this is problem 10, chapter 2. And so what we have 2 cars that are traveling along the highway. And just try to delete this thing here. Okay. So I have 2 cars traveling along the highway. And one's traveling at 55 miles per hour, one's traveling at 70 miles per hour. So these just represent the speeds, velocities. 50, just check it out here, 55 miles per hour. And this one's traveling at 70 miles per hour. And so what they're asking, assuming they start at the same point, which we have assumed here, how much sooner does the fast car arrive at a destination 10 miles away? So let's write an expression down for velocity is equal to the change in displacement divided by the change in time. So we know the velocities are positive. We're going to define x positive in this direction. And this is going to be x equals 0 right here, where they start.
So we're given the velocities and we're given the displacement, which is 10 miles. So what we're looking at is the time. So let's say the amount of time requires 55 miles per hour. So I'll use a subscript to represent that. Delta time, 55 miles per hour. What we do is, this is kind of like a ratio. And so in these ratio type situations, you can exchange the numerator and the denominators to different sides. So you can't do them on the same side. I can't just flip delta t up here and delta x there, but I can exchange v with delta t or delta x with 1 if I want to. So what I want to do is I want to solve for delta t. So that moves up here, and then I move the v down. So I get delta x over v. And the distance is 10 miles. So let's write that down. So delta x is 10 miles. So 10 miles divided by velocity, which is 55 miles per hour. And so the miles cancel out, and you end up with units of just hours. So it's going to be a fraction of an hour, which will convert to minutes. Just to 10 divided by 55 is 0.1818 hour. And if you don't multiply by 60, you'll get minutes. So we get 10.91 minutes. And the amount of time it takes to go 10 miles, traveling at 70 miles per hour. I think it's less time, of course. That. And so we get 0.1428 hours. We multiply by 60, so times 60 is 8.57 minutes. So the question is, how much earlier does this car get there than that car? Well, it gets there the difference. So we take 10.91 minus 8.57. So once that guy arrives there, he's waiting a certain amount of time. 10.91 minus 8.57. And so we get 2.34 minutes. So that's the answer for part A. How far must the faster car travel before it has a 15-minute lead on the slower car? So that was a little more difficult to think about. But what we want to do is we want that the difference between the two times, t at 55 minus t at 70 equals 15 minutes. And so the times here are equal to, I could put a delta t here, maybe delta t. So delta t 55 is the delta x divided by the speed, which is 55. And we subtract so it's still delta x at 70. And the difference has to be 15 minutes. Well, this worked out units of hours, so I'm going to use 0.25 hours. That's 15 divided by 60. And so now we just have to find the distance, delta x. Okay. So let us do that. So what would we do? We can find a common denominator. Just trying to think about how we would do this. The easiest way would be to multiply. Let's multiply by 70. So multiply by 70, we'll have 70 over 55 times delta x minus delta x is equal to 0.25 hours times 70 miles per hour. And so you have 70 divided by 55 is 1.27. And then we subtract 1, we'll have 0.2727. Delta X is equal to 70 times 0.25.
Recording started.
Okay, sorry for the delay. I got a phone call, so I need to take that. So what I was doing is multiplying 70 by 0.25, which was 17.5. And then you divide both sides by 0.02727. So you get 17.5 divided by 0.2727. And we get 64.2 miles. And so what it means is if you find out how much time it takes to travel, so let's just confirm this is true. So when this guy has traveled 64 miles, 64.2 miles, so it takes 64.2 miles divided by 70 miles per hour, 64.2 divided by 70 is 0.917 hours. And when this person has traveled 64.2 miles at 55 miles per hour, we get 64.2 divided by 55, and we see that it takes him 1.167 hours. And if we take the difference between these two, 1.167 minus 0.917, minus 0.917, I get 0.25 hours. And if you multiply 0.25 times 60, 0.25, there's 60 minutes per hour. So this is hours, this is minutes per hour. Hours cancel out, you get minutes. And a quarter of an hour is 15 minutes. So that's how it works.
Recording started.
Okay, this is problem 14. It's one of those blue problems. The tortoise can run the speed of 0.1 meters per second, and a hare can run 20 times as fast. So the speed of the tortoise is 0.1 meters per second. The speed of the hare is 2 meters per second. It's 20 times as fast. In the race, they both start at the same time, but the hare stops to rest for 2 minutes. The tortoise wins by a show. How long does the race take? So basically what we have is we're going to have, here's the starting line, and the speed of the tortoise and the speed of the hare. Of course, if this hare didn't rest, the hare would win because he's going faster, but he's going to stop. And he's going to realize, I need to get going, and then he loses by 20 centimeters. So the distance that delta x that the tortoise travels, because he doesn't take a rest, his distance is just going to be equal to the speed of the tortoise times the time. And the time is a constant between the two equations. And this comes from just the speed is defined as delta x over delta t, or sometimes we just put delta x over t because t usually starts out at 0 at the beginning of things like this. So sometimes delta t is just the time. Okay, now as far as the hare is concerned, the distance he travels, again, is his speed times the hare. But what we do is we take the time that takes to finish the race minus 120 seconds because he waits for 2 minutes. That's what it says, 2 minutes, which is 120 seconds. 2 times 60 is 120. So while the hare is running, The only time he's running is the difference between the final time and his 120-second rest. And we also know that the difference, the distance the tortoise travels and the distance the hare travels is 20 centimeters, which is 0.20 meters. We take 20, we divide by 100 to get from centimeters to meters, so you have 0.2 meters. So what do we have? We have three equations. And how many unknowns? We have 1, 2, and 3. We know the speed of the tortoise, we know the speed of the hare. We know that the tortoise wins by 20 centimeters. So we have three equations and three unknowns. And the best way to solve this is by just plugging in delta x sub t here and delta x sub h there, and everything will now become in terms of time, and we can work out how long it takes for the race to occur. So if we substitute for delta x sub t, we put in the speed of the tortoise times the time, and we subtract off the speed of the hare times t minus 120. That's delta x sub t. Delta x sub h is that. And that difference has to be 20 centimeters, which is 0.2 meters. So now all we have to do is solve for t. So if we take s sub t minus s sub h, and we multiply by t. So what I've done is I've taken this term and this term, and I've factored out t. And so what we have left is negative s sub h times negative 120, which is, so that's a positive 120 times the speed of the hare. And that has to equal to 0.2 meters. We subtract 120 times s sub h for both sides, so we get 0.20 meters minus 120 times s sub h. And then we divide both sides by this term in parentheses, so we have 0.02 meters minus 120 times s sub h divided by this quantity here, s sub t minus s sub h. So now we just need to plug in. So we have 0.20 meters minus 120 times the speed of the hare, which is 2.0 meters per second. This has units. 120 is a time. So you have time times seconds times meters per second gives you meters. And then we divide by s sub t, the speed of the tortoise, which is 0.10 meters per second. Subtract 2.0 meters per second. So we have meters divided by meters per second. I'll give us seconds. So now we do the calculation. 0.2 minus 120 times 2. And we divide that by 0.1 minus 2. And the time we get is 126 seconds. So the hare actually only runs for 6 seconds. And then he rests for 2 minutes and finally decides you better go across the finish line. Okay, so that's the answer to part A. How long does the race take? And what is the length of the race? Well, all we have to do, we could either do either one of these. We'll use the one that's the simplest one. Well, actually, we couldn't use the second one because that would just tell us how far the hare is, and we'd have to add in 20 centimeters to that, or 0.2 meters. So let's just use the first one. So the distance the tortoise travels is the speed of the tortoise, which is 0.10 meters per second. And that's multiplied by the time, which is 126 seconds. Seconds cancel out. That leaves us units of meters. And so 0.1 times 126 is 12.6 going to check the answer out here. Okay, so we're in good shape.
Recording started.
Okay, this is problem 18. And it gives us the position of a race car as a function of time, 5.0 meters per second times t. And I guess it actually is seconds cubed on the second thing. I realized that when I looked at the units. So now we have 0.75 meters per second cubed times t. So you can see if I multiply by t, that's seconds, then I get meters. And if I multiply by seconds cubed by this, I'll get meters as well. So, and then meters plus meters equals meters. So the units are correct. And what we're going to do is we're going to use this expression for the instantaneous velocity by taking the position on either side of 4. So our position, or actually our time, is going to be equal to 4.0. That's what we're trying to find the instantaneous. We're going to approximate it by going higher than 4 seconds. So we'll go to 4.4 seconds. Then we'll go the same units in the other direction. So that's 3.6 seconds. So that's the first part. And then we go to 0.2 seconds. So we go 4.2 and 3.8 would be our range. And then go from 4.1 and 3.9. So now if we plug these values in for t, then we'll get the corresponding x values. And I've done this on my calculator using this table. I started at 3.6 and gone by 0.1. So you can hopefully do that too. If not, you just plug them in and calculate them. So at 3.6, actually go down here, 4.4 seconds, we have 85.89. Let's go down to this 4.2 next, which is 76.57. 76.57. And then we go 4.1, which would be this entry, 72.19. And then we evaluated at these lower times, which should be lower. So delta x low, we go to 3.6 seconds in our table in the calculator. We get 52.99. At 3.8 seconds, we get 60.15. And then we go to 3.9 seconds, which is 63.99. Okay, and actually we have a delta t, well, the total time change, I'm just trying to decide whether this is the total one or we should go one more table element. Let's go to 0.05 and do 4.05 and 3.95. So we handle this. So I'm going to reset my table thing here so that it increments by 0.05. So here, 4.05, I get 70.07. And at 3.95, I get 65.97. Okay. So what we're going to do is we're going to use the formula that the velocity equals delta x over delta t. And in this case, delta t is actually double these. So this is just either side of 4 seconds. So really delta t is 0.8, 0.4, 0.2, and 0.1. So all we have to do is take delta x. So we take the high value minus the low value divided by 0.8. So if we do that, we take 85.89 minus 52.99, and we divide by 0.8. We get a velocity of 41.1. and this would be meters per second. Second case, we take 76.57, subtract 60.15, we divide by 0.4 in this case, and we get 41.05. Next, using the next row, 72.19 minus 63.99. We divide by 0.2 in this case, and we get 41.00. And then the final one is we take 70.77, we subtract off 65.97. We divide by 0.1, and we get we get 48, which doesn't seem quite right. Just because these are all kind of going down, all of a sudden it jumped to 48. So let me just put it on hold here for a second while I figure out if I made a mistake in copy or something like that.
Recording started.
Okay, I'm back again. It turns out this one is 41.0. Let me erase these extra significant figures, but so you can see that we quickly are approaching a value. So this turns out fairly linear in the small range of delta t. So the question problem was, plot the graph of car position versus time, which I haven't done yet. Determine the instantaneous velocity of the car at t equals 4 seconds. Compare the average velocity during the first 4 seconds with the results of part B. So the average velocity for the 4 seconds at t equals 0, v is equal to 0. If you plug t equals 0 here and 0, you get 0. And if you plug in t equals 4, you get, what do you get? You get 5 times 4 plus 0.75 times 4 cubed. And actually, I can just look at my table. 68. So we get 68. Actually, that's not the velocity, that's the distance. So the distance is 68 meters. This is 0 meters. So the expression for average velocity is just the total distance traveled, which is 68 meters. We start at 0 and we go to 68. And we divide by the time, which is 4 seconds. 68 divided by 4. 68 divided by 4. If I can do this right, 68 divided by 4 is 17. So the average velocity is only 17 meters per second, but the instantaneous velocity is 41. So what I'm going to do is I'm going to open up a graphing program, and then we are going to share that with you. So right now you'll have a blank screen, but I just wanted to, what we can do is, okay, here we go. Okay, so there's the graphing program. And what I'm going to do is I'm going to put in the equation that we have, which is, and I'm going to put in the independent variable, in this case is x. So I have 5x plus 0.75 x cubed. And what I'm looking for is I'm going to, from x equals 0 in this case, which is equivalent to time, up to 5. Y goes from 0, and it was equal to like 100. Let's put 100 in there. Okay, so there we go. Here we are at x equals 4, and the displacement is 68. And if you take the average velocity, it's basically going to go, you're going to draw a straight line from here to here. the slope of that line, if I can draw it, the slope of this line is going to be equal to the average velocity between 0 and 4 seconds, which I think I remember was 17. Yes, 68 divided by 4 is 17. Whereas the instantaneous velocity is the slope of the thing right there. And we found out that one is 41, which is a little over 2 times the slope of that, which looks like about right. And what we did was we went down to 3.6, which is about right here, and we got an x value. And then we went to 4.4, which is right here. We got another x value. If you draw a straight line between those two, the slope of that straight line is going to be the instantaneous or approximation of the instantaneous velocity. And as we move closer and closer to 4, we make the delta x smaller. These instantaneous velocities become closer and closer to the actual instantaneous velocity at that particular point. Now I'm going to show you something that, once I share this back again, this is something we'll learn in calculus. It turns out in calculus you can calculate the velocity by doing what's called taking the derivative. And the derivative of this expression we'll find out is 5.0 plus 0.75 times, we take the exponent of here, 3, and then we multiply by t squared. So we reduce the exponent by 1. And we multiply by the exponent. So that'll be the velocity. So if we put the velocity at t equals 4 in there, we will get 5.0 plus 0.75 times 3 times 4 squared. 5 plus 0.75 times 3 times 16. 4 squared, and we get 41 meters per second. And that's what we got when we moved closer and closer. So the change in time was smaller and smaller, and the instantaneous approximation gets closer and closer to the actual velocity, which we're using calculus here. You're not going to be responsible for that, but when you see that later, you'll understand what we're doing in calculus.
Recording started.
This is problem 23 from chapter 2. And this is the first of many problems using the motion, equations of motion. And actually, this is section 2.3, which uses the definition of acceleration. So we haven't come up with the equations of motion yet. So let's just use the definition of acceleration. And the acceleration is change in velocity. So I'm going to say it's, let's change the subscripts here for the time being. So this is my initial, this is my final. So you take the final velocity minus the initial velocity divided by the time that it takes to make that change, and that's the definition of acceleration. So it says, how long does it take for a car to go from 55 miles per hour to 60 miles per hour, assuming the acceleration is 10.6 meters per second squared? Well, the first thing we should notice is that here we have meters per second squared, here we have miles per hour, so we need to convert miles per hour to meters per second. And the easiest way to do that is to go to the beginning of the book and look for something there. We have miles per hour, this conversion factor down. So 1 meter per second is equal to 2.237 miles per hour. And we're always trying to just get the quantity 1. So to get 1, we have to divide both sides by meters per second. So we get 2.237 miles per hour per meter per second.
So now if we want to convert 55 miles per hour to meters per second, well, if we multiplied by this quantity, then we would have miles per hour squared divided by meters per second, which we don't want. So we're going to go the other direction. What we want is miles per hour in the denominator and meters per second in the numerator, because that'll give us meters per second when these cancel out. But we can still write this in. There are 2.237 miles per hour per 1 meter per second. So we take 55 divided by 2.237, and we get 24.6 meters per second. And we do the same thing for 60 miles per hour. We divide by 2.237 miles per hour per meter per second. So 60 divided by 2.237, and we get 26.8, which is good because this is larger than that, so this should be larger than that. Okay, so now we can just solve for delta t. So delta t, again, I always do in my head is I make this a ratio, and then I just can move these around. So I can move that down there, and I move that up there. I can move that up here and move that down there. So, or I can multiply these two together and those two together. In this case, I'm trying to solve for delta t, so that means that I want just delta t on the left-hand side. So I'd multiply this by 1, this by 1, and then I would divide by a. So I would get v final minus v initial divided by a. So that's delta t. And so we can plug in the numbers. So we have 60 miles per hour, which is 26.8 meters per second. We subtract off the initial speed, 24.6 meters per second. And we divide by acceleration, which is 10.60 meters per second squared. The meters will cancel out. All of the seconds will cancel out, and we just end up with seconds. So 26.8 minus 24.6 divided by 10.6, and we find the time is 0.208 seconds. So that's the amount of time it takes. And let's just check the answer. This is problem 23. So it's going to... Okay. What did I do wrong? Something wrong. Oh, it's not 10.6, 0.6. How did I read that wrong? Oh, it's because it's a typo in the book. Okay, so using the book, if I go back and I look at the solution, I see they use 0.6 meters per second squared. And in some ways, I should have realized that earlier because this is like 1g, which is a heck of an acceleration. So if you use 0.6 meters per second squared, you would get delta t is 26.8 minus 24.6 divided by 0.6, which is a slower acceleration. So let's plug that in. 26.8 minus 24.6 divided by 0.6, 3.7 seconds. Okay, so let's see, we're on problem number 25, chapter 2. So let me get my stuff ready here.
let's just read the problem. It's on page 50. It says a steam catapult launches a jet aircraft from the aircraft carrier John C. Stennis, giving it a speed of 170 miles per hour in 2.5 seconds. Find the average acceleration of the plane. Assuming the acceleration is constant, find the distance the plane moves. Okay, so a couple things. Let's just draw a picture of what's happening here. It doesn't have to be spectacular. So there's our aircraft carrier. Here's our airplane. It's pretty pathetic. With the bird. Anyway, it starts here from rest. So V0 is 0. And we're going to use feet per second. The plane speed is, the final speed is given in miles per hour, but we're going to convert that. So let's get right to the end. And so V, the velocity at the end, is 175 miles per hour. And it says the time it takes is 2.5 seconds. So what's the first thing we're going to do is we are going to convert miles per hour to feet per second. And you do that by going to the front of the book and find the conversion factor. So what you see is 1 mile per hour is equal to 1.47 feet per second. Or, if you just want to have a number, 1, if we divide by miles per hour, 1.47 feet per second per mile per hour. So if I divide by this on both sides, the units, I get 1 on the left-hand side. So that's dimensionless number. So if we want to take a velocity, 175 miles per hour, and what we want to do is to multiply it by 1.47 feet per second per mile per hour. And you see we have miles per hour in the numerator, basically miles per hour in the denominator, so this cancel out. And so we have feet per second, that's the final answer. So when you take 175 times 0.147, 175 times 1.47, we get a speed of 257 feet per second. And I kept 3 significant figures because there's 3 here and there's 3 there, so there's 3 in the final answer. I rounded down. Okay, now, if we assume constant acceleration, the average acceleration is going to be equal to V minus V0 over T. It's just from the definition of acceleration. Acceleration is change of velocity per unit time. So we have 257 feet per second minus the initial speed, which is 0 feet per second. And we divide by the time, which is 2.5 seconds. So when you take feet per second divided by seconds, you get feet per second squared, which is the units for acceleration. So we get 257 minus 0, which is, of course, 257, divided by 2.5. And the acceleration is 102.8 feet per second squared. So that's the acceleration. It's positive because we're speeding up. And also, if you think about it in terms of G's, acceleration due to gravity turns out to be 32.2 feet per second squared. So the number of G's would be taking this divided by the acceleration due to gravity. So I'll just say G's. So I divide that number, so I get 3.2, basically 3.2 G's. Which seems reasonable. Okay, so that's the acceleration. Now, that's just from the definition of acceleration. So the next question was, lost my place here. Okay, Assume the acceleration is constant, find the distance the plane moves. So we have the four equations, and one says that, see if I can remember these. This is about just before school starts. And so there was one that says, you take the average velocity and you multiply it by time, that's going to be equal to x, the displacement. We also have that the velocity at some time is v0 plus a times t, which is really just using this equation, solving for v. We have that x, or delta x probably better use, the change in displacement is equal to v0 times time plus 1/2 a acceleration squared. And these are all only good when the acceleration is constant. And then you get v squared is equal to v0 squared plus 1/2 a times delta x. So those are the four equations. And the question is, which one do we need to use to find the displacement? Well, we could use either one of these. And let's just prove we get the same answer. But this is the one I would use because it's the easiest one. So delta x is v, which is 257 feet per second, plus 0 feet per second, that's the initial velocity, divided by 2 times 2.5 seconds. So delta x is 257 times 2.5 divided by 2. 321 feet, which is about the length of a football field. And we're going to just use three significant figures. The other one is this equation, so let's just try that. I'm trying to think if there's any reason we can't use that. No, I can use it. So delta x is v0, which is 0 feet per second, times the time, which is doesn't really matter because it's times 0, 2.5 seconds plus 1/2 the acceleration, which is from the previous problem, 102.8 feet per second squared times time squared, 2.5 seconds squared. So we get 0.5 times 102.8 times 2.5 squared, and I get 321 feet, which I should have gotten because I said I get the same answer. So you can see it doesn't matter which one we use. Okay, so that's it. Okay, we're doing problem 31. And I actually worked through it one time, and I copied an equation wrong, or just forgot wrong. It's been a while since I did this stuff. So I'll point out where I made a mistake as I go through, and then we'll correct it. So here's the problem. We have a Cessna aircraft that starts at 0 meters per second, accelerates at a constant value until we get 120 kilometers per hour minimum for takeoff. So we have to accelerate enough so we get to this point. Now this point, the displacement is 240 meters from start to where I need to take off. So the first thing I'm going to do is I'm going to convert kilometers per hour to meters per second. We always try to convert to feet per second or meters per second, and then go from there. So to do the 120 kilometers per hour, we go to the front of the book and we find out that 1 kilometer per hour is equal to 0.278 meters per second. So if we divide both sides by kilometers per hour, we get that 1, which is unitless and just a unity and unitless, 1 is equal to 0.278 meters per second per kilometer per hour. So that's one conversion. The other conversion is 3.6 kilometers per hour per meter per second. What I do there is I just took kilometers per hour, put it in the numerator, meters per second, put it in the denominator, and to do that you have to take the reciprocal of this number. The reciprocal of 1 divided by 0.278 is 3.6. Now, I'm not sure which one I need yet, so we have to just look at the conversion. So we start with our known, 120 kilometers per hour. We multiply by this expression, There are 0.278 meters per second per kilometer per hour. And this is the one we choose because I have kilometers per hour here. Say this is the numerator, and then you have the line, and the denominator is kilometers per hour. So these cancel out, and we just end up with meters per second. So this is the correct units. So we take 120 times 0.278, give us 33.4 meters per second. So that is the final velocity for takeoff. Now, let's see what we know. We know the initial velocity, the final velocity, and the displacement. So we know 3 out of the 5 things that we need to know. So we can calculate them. We know these 3 things, but we don't know the acceleration or the time. So the thing is to write down the 4 equations. And the one I got wrong here was this one right here. Should be 2a delta x. And actually, I wrote it wrong in the last problem, but I never used it, so it didn't show. I didn't realize it. So it's plus 2, not plus 1/2. Okay, so which ones can we use? We need to solve for acceleration and time. And we don't have to necessarily do it in the order that they tell us in the book. We can do time and then acceleration, but in this case, it doesn't really matter that much. So of all these, the only one that has these things, the acceleration, the velocities, and the displacement is this one. All the other ones have time in it, which we don't know what the time is, so that just doesn't help us at this point. So this is the equation we use, and what we do is we solve this algebraically for the acceleration. So if we do that, and we correct my error here, if we subtract v0 from v0 squared from both sides, we get that. And so what we're going to do is we're going to divide by, so we divide by 2 delta x. That'll leave us with acceleration on the right-hand side of the equation. So if we do that, we get this expression. So it's the quantity v squared minus v0 squared all over 2 delta x. So now we know everything over here, and I'm going to plug it in. So this should be in the denominator. And the units work out correctly, so you get 33.4 squared divided by 2 divided by 240. So we get 2.32. I was off by a factor of 9 because I had it in the wrong place. So you get 2.32 meters per second squared, which actually is not, I mean, it's not anything like being thrown off the aircraft carrier. The aircraft carrier was 100 something, well, actually it was feet per second, so it's not exactly. This is it's about a quarter of a G, and that was like 3 Gs, I think, so it's about 12 times difference. Okay, so the time, now we can use any of the other ones to solve for time. This one's the simplest one, so I'm going to solve for time from the second equation, the one right there. And if I put the right time in the right acceleration, 2.32, we take, so we have 33.4 minus 0, which is 33.4, divided by 2.32, which is 14.4 seconds. And the units work out okay because we have meters per second here, divided by meters per second squared. That's equivalent to meters per second multiplied by the reciprocal of this term. So you get seconds squared over meters. This goes down, this goes up. The m's cancel out, the meters cancel out. One of the seconds cancel out, and you're just left with seconds. So that is the right answer now. Pretty sure, yep. So we're good. Okay, where are we? Number 37. So we have, let's just read it. Problem number 37. So we have a train. It's traveling down a track. Traveling down a straight track
20 meters per second. So V0, 20 meters per second. When the engineer applies the brakes, resulting in acceleration of negative 1 meter per second squared. So the acceleration is negative 1.0 meters per second squared. It's negative because it's slowing it down, reducing the velocity. And it has that acceleration until the train stops. How far does the train move? During a 40-second time interval, starting at the instant the brakes are applied. So we have a time equal to 40 seconds. So we have three things. The only question is does this thing stop before 40 seconds? So what we would do really is we would say, okay, this is our starting point. Let's see, let V equal 0. And then we can figure out from this being 0 and this being acceleration, you can find out what the time is. And if the time is greater than 40 seconds, then we know that it doesn't stop. If it stops in less than 40 seconds, then that's as far as it's going to go, because the brakes don't make it go backwards, they only slow it down. So let's see, which one of these, let's write equations down. Delta x is equal to V plus V0 over 2 times the time. V is equal to V0 plus AT. Delta x is equal to V0t plus 1/2 AT squared, and V squared is equal to V0 squared plus 2A delta x. So which one of these involves V0 acceleration and time? Well, this one does. So let's see what happens here. Just thinking if that's the right one I want to use. The only issue here is you have to use the quadratic equation to solve for it. Actually, this one's easier. I think we use all the same stuff. So, yeah, let's just use that one. So we'll find the time. So the time is V. Subtract V0. And then you divide by A. So V is 20 meters per second. Pardon me, V0 is 20 meters per second. V0 is 0 meters per second. Acceleration is negative 1.0. I did that wrong in the end, didn't I? V is 0. 0 meters per second minus V0, which is 20 meters per second. That's the initial speed. I know I did it wrong because I was getting a negative time. You never get negative times. Okay, so if you take negative 20 divided by negative 1, you get 20 seconds. So what's going to happen is it'll stop after 20 seconds and then it'll sit for another 20 seconds. It won't go anywhere. So all we have to do now is how far does the train go down the track? Well, it only goes down the track for 20 seconds. So we know that V0 is equal to 20 meters per second. We know the acceleration is negative 1.0 meters per second squared, and we know the time is 20 seconds. That's the only time it's traveling. And now what we want to do is find delta x. So which equation uses this, and that? Well, this one doesn't have delta x. This one has delta x, but it doesn't, we can't find it. Well, I guess you could use that one. Let's see why not. We could also use this one directly. And we don't know the time. Well, we do know the time. It's 20 seconds. So I guess there are a lot of different ones that we can use here. Seems like there's too many. What is that? We know here that v is equal to 0 meters per second. So that's why we can use sum m, because we really know 4 things. And so you can pick any 3 or 4 of the equations. So I'm going to use delta x is equal to v plus v0 divided by 2 times the time. And again, I could have used a lot of other ones. So we have v, which is 0, plus v0, which is 20 meters per second. And we divide by 2, and we multiply by the time, which is 20 seconds. And so we get 20 meters per second times 20 seconds divided by 2. And so we get 200 meters. It's meters because we have meters per second. We multiply by seconds, the seconds cancel out, and we just have meters per second. So delta x should be 200 meters. But let me just check the solution. Okay, we have problem 41, chapter 2. So let's open up our book. And this is another blue problem, which is an intermediate difficulty. This is in a Daytona 500 race, a Ford Thunderbird and a Mercedes-Benz are moving side by side, which is kind of strange because you really never have a Mercedes-Benz in Daytona, but I don't think you do. Anyway, they're moving side by side down a straightaway, 71.5 meters per second. The driver of the Thunderbird realizes that she must stop, make a pit stop, and she smoothly slows down to a stop over a distance of 250 meters. She spends 5 seconds in the pit and then accelerates out, reaching her previous speed of 71.5 meters per second after a distance of 350 meters. At this point, how far has the Thunderbird fallen behind the Mercedes-Benz, which has continued at a constant speed? So what we can do is if we can figure out how much time it takes for the person in the Thunderbird to do all those 3 things, and then we know the distances it's traveled, and then we can use that total time to see how far the other car has traveled, then we should be able to take that distance and distance traveled and calculate the difference. So let's draw our race car, and here's the pit stop. We'll assume that the distance of going along the track is the same as the distance in the pit stop. So here we start. Let's say this is 1. And so then if we slow down to 2, and then 3, 2 and 3 are both in the same location because it's time that it's just sitting there. And then we come back up here to 4. So those are the 1 to 2, 2 to 3, 3 to 4. And then the other car is just going to be going straight. And it'll end up being ahead, of course. So let's look at different places. What we're going to do is add up all the times it takes to each one of those, and then we'll use that time to figure out what's going on. Okay, so from 1 to 2, what do we have happening? Well, we have a V0 of 71.5 meters per second. We have a V of 0 meters per second because they slow down, and the distance, delta x, is 250 meters. So we can calculate the time. So we'll call it T1 to 2. Then 2 and 3, it's just V is equal to V0, which is equal to 0 meters per second. And that takes how much time? So T from 2 to 3 is equal to 5 seconds. And then from 3 to 4, V0 is equal to 0, because we start from a standstill. We speed up to 71.5 meters per second. The delta x is going to be 350 meters. And from that, we can calculate the time it takes to go from 3 to 4. So we're going to have then these three times added together, would give us a total time. We know that the car has traveled 250 plus 350 meters, or 600 meters. Then we'll find out how far the other car is driven during that time period. So that's the plan. Sounds like a good plan to me. So again, writing the equations down, delta x is equal to v plus v0 over 2 times t. Is that the one we want to use? V0, yeah, looks like it. So we don't need to write those down. So we get t is equal to 2 delta x divided by v minus v0. If we do the algebra, you take 2 and you multiply both sides, so you get 2x, and then you divide by this, and you solve for t. And so the time to go from 1 to 2 as we slow down is going to be equal to 2 times delta x, which is 250 meters. V is equal to just make sure I think about this. Oh, it's plus. I knew there was something wrong. So V, which is the final velocity, which is 0 meters per second, plus the initial velocity, which is 71.5 meters per second. And if we do that, we get 2 times 250 divided by 71.5, and that's about 7 seconds, 7.0 seconds. To go from 3 to 4, we have to go 300, it takes us 350 meters. It's harder to accelerate than it is to decelerate. Our V is going to be equal to 71.5. Our V0 in this case is 0, so they switch places because one's slowing up, one's slowing down. So you take 2 times 350 divided by 71.5. We get 9.8 seconds. So the total time to go from 1 to 4, which is from slowing down, sitting there, and speeding up, is going to be 7 seconds plus, we get 5 seconds sitting still, plus 9.8 seconds, for a total of 7 plus 5 plus 9.8, 21.8 seconds. Okay, so that's the time. Delta x, going from 1 to 4, is 600 meters. Now, the other car is going at constant speed, so the equation there, it's not constant acceleration, but constant velocity. Delta x is equal to v times t. So the distance, the car that doesn't stop, is going 71.5 meters per second times the time, which is 21.8 seconds. 71.5 times 21.8 is 1,560 feet, or meters. And so the net difference is going to be the distance the car that's going constant speed travels minus the distance the other car travels. So you get 960 meters. If I did that correctly, hopefully I did. Let me just check the answer. Yes, I said 958. That's close enough. Okay, so that's the deal. Let's just kind of review what we just did. We took one car is going to go around at constant velocity. The other one's going to slow down, sit there, and speed back up. So we looked at the case of the one that did the pit stop. Started at 71.5 meters per second, stopped 0 meters per second, took 250 meters. you can calculate the time from one of the four equations. While it's sitting there, it's not moving, there's no speed, there's no delta x, 5 seconds. Then you go from 0 speed to max speed. It takes 350 meters to do that. You can calculate a time for that. So we did that using this particular equation, solving for t. Then it was 7 seconds to slow down, 9.8 seconds to speed up. And therefore, the total time it would take is 7 plus 5 plus 9.8, which is 1.8 seconds. And the total distance traveled is 250 plus 600, or 250 plus 350, which is 600. The car that's moving without the pit stop goes at constant velocity for 21.8 seconds. It travels 1,560 meters. So the difference in the distances traveled, 1,560 minus 600 is 960 meters, and that's how far the thing will be ahead. Okay, so that's it. Okay, so we're doing number 45, which is the first of the free-falling object problems. The thing about free-falling object is we know the acceleration. So in this case, the acceleration is going to be negative 9.8 meters per second squared. That's acceleration due to gravity. And so it says a ball is thrown vertically upward with a speed of 25 meters per second. How high does it rise? Well, it's going to rise until the velocity goes to 0, and then it's going to go the other way. So it starts here at some speed, and as it goes higher, it gets lower and lower speed. At some point it goes 0, and then it starts going the other direction. So for our particular case, V is 25 meters per second. And V0 is equal to, actually, that's the wrong way around. V is equal to 0, and V0 is 25 meters per second. And it's positive because we have to define positive and negative. So if you think about this, we're going to let y going up be positive. Actually, y going up being positive. So since we throw it up, it's going in the same direction as the positive y direction. So V0 is positive. A is negative because it's going downward. It's an acceleration to pull you back to Earth. So now we have three pieces of information, and we can calculate everything else. So let's write down the equations. Delta x is equal to V plus V0 over 2 times time. V is equal to V0 plus AT. Delta x is equal to V0t plus 1/2 AT squared. And V squared is equal to V0 squared plus 2A delta x. Now in this case, we're actually using delta y. It's all in one dimension. So what do we need to do here if we want to find, say, delta y? Find delta y, knowing V, V0, and A. I think it's this one. Yes, it is. Okay. So let's rewrite that. Instead of in terms of x, we'll do it in terms of y. So I'm just changing delta x to delta y. And if we solve for that, the first thing we do is we subtract V0 squared from both sides. So we get this. And then we divide by 2a to get delta y by itself. So we get delta y is equal to this quantity here, v squared minus V0 squared divided by 2a. So that's what we want to do. So the height is equal to V squared, which is 0 meters per second. So that's our final velocity where it goes to 0. We have negative V0, which is 25 meters per second. And we square that. and we divide by 2, and we divide by negative 9.8 meters per second squared, second squared in the units. And you can see the negatives are going to cancel out, so we get a positive delta y. And so we have 25 squared divided by 2 divided by 9.8. And so we get 31.9. So delta y is 31.9 meters. Now we know it's delta y is meters because distance is meters, but you could do it from the units as well. You get meters squared per second squared when you square this, divided by meters per second squared. Second squared's canceled out, and you just have meters squared divided by meters, which is meters. Okay, so that's delta y. What's the next thing they're asking for? How long does it take to reach its highest point? Okay, well, we just use one of these other equations. There's not any that originally solved for t, but this one looks like a good one to solve for. And if you do that, you get v minus v0 over a. So the time is v, which is 0 meters per second, the peak, the velocity of the peak, minus v0, which is 25 meters per second, divided by the acceleration, which is negative 9.8 meters per second squared. And so we get 25 divided by 9.8. Negatives cancel out, and we get 2.56 seconds. So that's how long it takes to go from ground to its maximum height. How long does the ball take to hit the ground after it reaches its highest point? Now, that's one thing about these vertical problems is they're symmetric. So you throw a ball up, it goes up here, takes so much time, and then accelerates and goes back down. And it takes, this is half the time, and this is another half the time. So in this case, how long does it take the ball to hit the ground? It takes, so part C is, time it takes is 2.56 seconds. And we could do that, figure that out, because we still have the same acceleration due to gravity. It's just, the only thing that changes is we start off at, V is going to be 25 meters per second down. Actually, I mean, that's true, but I'm not sure if you guys know that. Let me think about this one. We didn't know the symmetry part. What do we know? Well, we know that V0 is equal to 0 meters per second at the top. We know the time is, we don't know the time. That's what we're trying to figure out. What else do we know? The acceleration is equal to negative 9.8 meters per second squared, and we know that the distance it travels up has to be the distance it travels down, so delta y is negative 31.9 meters. So what goes up must come down, same distance. And so you can do the same thing here. You can solve for t, or we could solve for v. Let's just solve for v. So v, velocity, which one of these equations over here do we want to use? So we know the acceleration, we know the velocity, we know the delta y. So we should be able to use this one right here. So v squared is equal to v0 squared plus 2a delta y again. And so we can solve for v squared is equal to v0 squared is 0 meters per second. 2 times the acceleration, which is negative 9.8 meters per second squared, times delta y, which is negative 31.9 meters. And see, the negative times negative becomes positive, so we get v squared is equal to 2 times 9.8 times 31.9. The negatives cancel out, and we get 625 meters squared per second squared. So if you take the square root, you get the square root of that is 25. Okay, so that's plus or minus 25. Because when you take the square root of something, it can be plus or minus. In this case, it's going to be negative because we know it's falling down, so it's actually the negative 25 meters per second. And as you can see, it's the same as the velocity that we had initially. It's just it's going down instead of coming up. So you can see the symmetry occurring. And then with that information, you could calculate the time using the same thing. Time is equal to V minus V0 over A. In this case, V is negative 25 meters per second. V0 is 0. Acceleration is negative 9.8 meters per second. And negatives cancel out. And you get 25 divided by 9.8. 2.55 seconds, 2.56 seconds, which is the same thing we got up here. So you can see it takes just as long to go up as it does to come down. What is the velocity when it returns to the level from which it started? Well, we already answered that question. 25 meters per second, but it's in the negative direction. So let me just check these answers out. Okay, so the bad news is that, for me at least, is I did this problem, and I realized I forgot to push the record button. So that's the bad news. The good news is I made a mistake when I did it, so this is with the mistake corrected. Okay, so this is problem number 50, and we'll read it. A small mailbag is released from a helicopter that is descending steadily at 1.5 meters per second. After 2 seconds, A, what is the speed of the mailbag, and B, how far is it below the helicopter? So, yes, I'm just thinking because I've got the two parts worked out at one time. Well, I think we'll be okay. So here's my helicopter, and here's the bag. And so the helicopter is moving down at 1.5 meters per second. And it's negative because it's moving down, because I defined y positive is going up. I'm going to define y equals 0 at the point where the bag is let go, rather than the ground, because there's no information about the ground. So we're going to do everything relative to when this thing's going down, and then when we reach this point, you let go of the bag and see what happens. And the bag does not hit the ground. We would have to know something about the distance of the helicopter from the ground to know whether it hit the ground or not. And so what happens is the bag falls for 2 seconds after it's let go. And the question is, what is the velocity after 2 seconds, and how far has the bag dropped, and how far has the helicopter dropped, and what's the difference between those two values, and that'll give us the distance between the helicopter and the bag. So the helicopter is under a constant velocity situation because it's continuing to go down at 1.5 meters per second. And under constant velocity, we really only have one equation that relates displacement and velocity in time, because acceleration is 0 under those conditions. And the equation is that delta y of the helicopter, the change in height of the helicopter, is the velocity, which stays constant, on negative 1.5 meters per second times the time. So that's just a simple equation. For the bag case, when we let go of it, it now goes to a constant acceleration situation, the acceleration being acceleration due to gravity. Okay, so we have 4 equations that apply. 4 equations that are delta y. And let's put delta y sub b here. So delta y sub b is the average velocity times the time. The velocity is equal to the initial velocity plus the product of the acceleration and the time. The delta y of the bag is also the initial velocity times time plus 1/2 acceleration times time squared. and the velocity of the bag squared is equal to the initial velocity of the bag squared plus 2a acceleration delta y of the bag. Now, if we want to see for the first part where our velocity is going down, to find the displacement of the helicopter, you take the velocity of the helicopter, negative 1.5 meters per second, multiplied by the time, 2 seconds. And so the helicopter drops 3 meters, goes down. Now the bag is going to go faster. It's like you drop the bag. When you let go of a bag in a helicopter, unless the helicopter is moving faster and accelerating more than the acceleration due to gravity, it's going to drop. Okay, so this is going to move faster. Our velocity is going to be higher. Ignore the blue for the moment. That's part B. Well, we can talk about it. Let's go ahead and do part B right now. So part B, the second part, the helicopter is moving up, and therefore the velocity is positive 1.5 meters per second. So in this equation, instead of using negative, we use positive. And so instead of going down 3 meters, it goes up 3 meters in 2 seconds. Okay. Now, to calculate the velocity of the bag, we're going to use this equation because we know the initial velocity of the bag is going down with the helicopter. We know the time, 2 seconds, and we know the acceleration, which is negative 9.8 meters per second squared. So plug those in. Negative 1.5 meters per second plus the acceleration, negative 9.8 meters per second squared times the time, which is 2 seconds. And if you plug that in, you find out that the velocity of the bag after 2 seconds is negative 21.1 meters per second compared to the helicopter, which is still at negative 1.5 meters per second. Okay, now, so that's how you get the velocity. To get the, let's go ahead and do this because the velocity of the bag, if the helicopter is moving upward, the only thing that changes is this becomes positive 1.5 meters per second. So we have positive 1.5 meters per second. The second part stays the same because we have the same time, the same acceleration due to gravity. And so its velocity after 2 seconds is negative 18.1 meters per second. So that's the difference. Because this is already going down and this makes it go down faster. This is going up and this makes it go down at the same speed. So the only difference is this up, down versus up. The difference, the net difference of 3 meters per second. Now, as far as the displacement is concerned, for the helicopter moving down originally, we have the 3 quantities, time, velocity, and initial velocity and acceleration. So we can use this equation, which is the third equation, and we just plug the numbers in. Negative 1.5 to 1/2 times negative 9.8 times 2 squared. And if you do that, you find out the displacement of the bag, which is the black one, is this part's negative 3, this part's negative 19.6 meters. The blue is what happens if the helicopter is going up initially, which is plus 1.5 meters per second. So this part becomes plus compared to minus. So this part changes, this part doesn't change. So we go from positive 3, or negative 3 to positive 3 meters, contributed by this initial velocity. The second part stays the same because it's just based on the acceleration on time, which is the same with both parts of the problem. So if you take negative 3 minus 19.6 meters, you get that the bag goes down negative 22.6 meters. The helicopter goes down 3 meters, negative 3 meters though. Now, if you have the blue case, which is the helicopter going up, the helicopter goes up 3 meters, and the bag goes down negative 16.6 meters. So what we do is we take the difference between these two numbers. So we take this minus that, and this minus that, and that'll give us the distance. So the difference in height between the bag and the helicopter is the change in height of the helicopter minus the change in height of the bag. So we take negative 3 minus a negative 22.6, which gives us 19.6 meters. So the helicopter actually is 19.6 meters above the bag. And if we do it with the helicopter moving up, which is the second case, we have +3 minus a negative 16.6 meters, and that comes out to be 19.6 meters, same number. So it doesn't matter whether we're going up or down, the difference, the relative difference between the helicopter and the bag stays the same. So, if you watch that bag fall in the helicopter, the bag would look like it's doing the same thing in both cases. If you were standing on the ground, you would see that the bag is not as close to the ground in this case when the helicopter is moving up versus the one that's going down. So it's like if you throw something down versus drop something, it's going to get to the ground faster if you throw it down. So, or if you were jumping up and then throwing down, it's going to be. But relative to the person, relative to the helicopter in this case, you still have the same difference. Okay, so I did remember to record that, thank goodness. Okay, this is 53, which is another red problem, and hence it is reasonably complicated. So I'll try to be as explicit as possible what's going on. So this is 53 again. So let's read it first. The model rocket is launched straight upward with an initial speed of 50 meters per second. It accelerates with a constant upward acceleration of 2 meters per second squared until its engines stop at an altitude of 150 meters. What can you say about the motion of the rocket after its engines stop? What is the maximum height reached by the rocket? How long after liftoff does the rocket reach its maximum height? How long is the rocket in the air? So there's really, let's just see what's happening here. So it's it's almost like the rocket is launched, not with, it actually has a rocket engine, but it also must be put in like a catapult or something like that. So here's our rocket. Okay, so there's our rocket. And so it starts with an initial velocity of, let's assume it starts from the ground. So we're going to say y equals 0 right here. And we're going to define positive y in this direction. So it starts with an initial velocity, v0, of positive 50 meters per second. Positive because it's going up, same direction as the positive y was defined. It's going to go up and it's going to accelerate, which means the velocity is going to increase to some point. Then the engine quits. But it's still going to keep going up because it has some it has a speed higher than 50 meters per second. So it'll keep going up and then it'll slow down as gravity pulls on it. And at some point it'll reach its maximum height where it will be 0. The velocity will be 0. And then once it gets to the top, then it will start to go back down and it will accelerate due to gravity until it hits the ground. And then when it hits the ground, then it will have its maximum velocity. So let's break it up in different colors. Let's do black for the first part, which is the acceleration part. So in this part of the thing where it goes up, the motors are working, we have an acceleration of positive 2 meters per second squared. We know that y0 is 0. We have the initial velocity, and it says, what does it say? It accelerates until the engines stop at an altitude of 150 meters. So we know that delta y, the black part here, is positive 150 meters. So we have three things. We have delta y, we have v0, we have acceleration. Okay. Now the second part is where it goes up here, it slows down, and then it finally gets to a peak. Okay, so that's the peak part. So here we have another initial velocity. We'll call it V0 blue. We don't know what that is, but V0 blue is equal to the final velocity, black. So you can't have a discontinuity velocity, so it has to go from the velocity right here at this interface when the motor stops is this velocity. Here's the new velocity for the second part. The acceleration for the blue part is negative 9.8 meters per second squared. So we have two things now. We'll get this from the first part. We know that. And we know that V is equal to 0 because it reaches its maximum when the velocity goes to 0. So we have three things there, so we're in good shape. Then let's do the red thing, which is when it falls. So then it falls down until it crashes into the ground. So what is V0 for the third part is 0. 0 meters per second, because that's what it was to the end here. The acceleration is still negative 9.8 meters per second squared. And delta y is going to be equal to 150 meters, which is this part, plus delta y from the blue part. So from here we're going to calculate delta y. We're going to calculate v. Actually, we already know v. We can calculate t. So we can also calculate t here, and we can let's circle what we're going to calculate. So we're going to calculate delta y and t. Here we're going to calculate t and v. And over here on the red part, we're going to calculate. We know delta y. We know acceleration. We know v0, so we can calculate how long it takes to fall as well. So we can calculate t if they asked us that. And we can calculate v, which is the velocity before it hits the ground. And the total time to go from the ground to here is going to be just the sum of these two t's, the blue t and the black t. Okay, so that's kind of the gist of it. Excuse me. So we just have to do the stuff now. And what I'm going to do is actually want to no, I thought I was going to do it. There we go. I'm going to group all that stuff. And there we go. And that way I can make it just a little bit bigger. Instead of doing that, I can actually move that over there, make it bigger so we can see it better when I add this extra page. So let's do each one of these separately. So now we're going to use this kind of visual thing. So for the black part, we had V0 is equal to 50 meters per second. And the reason I did that is I always had this fear of not recording it. This is a well-founded fear. Okay, so V0 is 50 meters per second. Delta Y black is 150 meters. And acceleration is positive 2.00 meters per second squared. And down here in green, we'll write the equations that we're going to use. So these are all constant acceleration situations. This is constant, constant, constant. So the equations are that delta y is equal to v plus v0 over 2 times time. V is equal to V0 plus AT. Delta Y is equal to V0T plus 1/2 AT squared, and V squared is equal to V0 squared plus 2A delta Y. So those are our four equations. Now we just have to play the game. So let's go ahead and calculate T. Actually, I think we're going to calculate V first. So V, we could use this equation. So V squared is equal to V0 squared. Oops, put the 0 in the wrong place there. V0 squared plus 2A delta Y. V0 is 50. So that's 2A, which is positive 2.0 meters per second squared, times delta Y, which is 150 meters. So we get 50 squared plus 2 times 2 times 150. So V squared is equal to 3,100, and therefore V is equal to the square root of that, which is 55.7 meters per second. This is meters squared per second squared. So that's the velocity. It's increased. Not a huge amount, but it has increased. And I'm just going to check the answer to make sure I'm doing this right first before we go too far. Okay, so that's right. So that's the velocity. So now we can calculate the time. Probably can use this one now. So if we solve for t, we get v minus v0 over a. V is 55.7, v0 is 50, divided by the acceleration, which is 2.00. And we did it correctly because we get a positive number. So we get 55.7 minus 50, which we should have done in our head, divided by 2.85 seconds. So that's T, black. Now, let's add a page. Add page plus page here. So we're going to do the blue part next. So what do we know about blue? Well, we know that the acceleration is negative 9.8 meters per second squared. We know that V0 is equal to positive 55.7, I think it was, 55.7 meters per second. And we know that V is equal to 0, because that's the peak. So now what we need to find is T and delta Y. So which one do we want to use here? Which one of these equations? Well, it looks like we could find T from this equation. And we could, once we get T, we can use this one to get delta Y. So let's do that. That's sometimes more than one way of doing it. That's the one I chose. Sometimes we try to avoid this one unless we're just plugging straight in, because we'd have to solve the quadratic equation, which is okay, but it's nice to avoid that if possible. Okay, so we're going to do V is equal to V0 plus AT, and we've done this before. We just did this in the previous problem, so it's V minus V0 over A. So V is 55.7 meters per second minus, oh, sorry, that's wrong. It's 0 meters per second minus 55.7 meters per second divided by the acceleration, which is negative 9.8 meters per second squared. And so the time is, should be positive, negative 55.7 divided by negative 9.8. It's 5.68 seconds. 5.68. Now, we can use the first equation to calculate delta Y. And so delta Y is equal to V, which is 0, plus V0, which is 55.7, divided by 2, times the time, which is 5.68 seconds. So delta Y is equal to 55.7 0.7 divided by 2 times 5.68, 158 meters. So what does that do for us here? Well, now we know that delta y here is going to be 150 plus 158. So let's go ahead and add another page in here. We'll do the red part now. What do we know? We know V0 is 0. We know that delta y is equal to negative, and actually I should put a negative sign there because it's going down. So it's negative 150 plus 158. So delta y is equal to negative 308 meters. So we got 2, and then what else do we know? We know the acceleration is negative 9.8 meters per second squared. And actually, I'm going to go back and read what they're asking for in a second, but I can do it with all the calculations ahead of time. So now what do we need to do? We need to figure out T and V. I think we'll use this one to get, no, that's not the one. It's probably this one here. I know the acceleration of delta y and V0, so I can solve. Okay, so I'm going to solve for V. So we're going to use it. We're going to use that equation, which I don't need to be in green. So we have v squared. The final velocity is the initial velocity, which is 0 meters per second squared, plus 2 times negative 9.8 meters per second squared times negative 308 meters. So that's going to be 2 times 9.8 times 308. The negatives cancel out. And we have 6,040 meters squared per second squared. Take the square root, we get plus or minus 77.7 meters per second. Now, because we know it's falling down, we can pick the negative version, so it's negative 77.7 meters per second. So that's velocity, and then knowing that, we can solve for time. So T is equal to V minus V0 over A. V is negative 77.7. V0 is 0, divided by the acceleration, which is negative 9.8 meters per second squared. And since we get positive time, we know we got all the signs correct. So we get 7.93 seconds. 3 seconds. So that's that part. Let me just make sure I did all this right again. 308 meters. Okay, I think I did it right. So let's see what they asked us now. I don't know what problem we're on now anymore. Number 53. Okay, what can you say about the motion of the rocket after its engines stop? Well, we can know that after the engines stop, it's basically in free fall, even though it's going up. It's kind of a weird way of doing it, but it's only acting under the force of gravity, and it goes up until the velocity goes to 0, and then it stops, and it starts going back down again. What is the maximum height reached by the rocket? Well, we got that. That was 308 meters. That was the displacement. And what we did was we added 150 plus this displacement gave us the total. So 150 plus 158. How long after liftoff does the rocket reach its maximum height? Well, all we have to do there is take this time plus that time. So let's pick those out. So we have those two right here. 5.68 plus 2.85. So for the total, time going up, I'm going to use green for that. The total time going up is the time, black time, plus the blue time, sorry, wrong color, plus the blue time. And so that's equal to 5.68 is the blue time. What was the other one? Oh, it's right here, 2.85. So we have 2.85 seconds plus 5.68 seconds. And so the total time is some of those two. 5.68 plus 2.85, that's 8.53. Make sure I did that right. And then the final question is, how long is the rocket in the air? Well, we take this and then we add another, we take the red time, which is 7.93 seconds. So we take 7.93 plus 8.53, we get 16.43 seconds. So total time in air is going to be 16.5 seconds. Make sure I did that right too. 16. I get 16.4. I get 16.5. That's probably close enough. Just a little round off air. Okay, so that's pretty much it. So let's kind of just review here what we did. Is we broke it up into three parts. When the rocket engine was pushing it, which gave us some altitude as well as a little bit more velocity. The engine cuts off. The acceleration due to gravity is pushing it, slowing it down until you reach the maximum height. And then at that point, it starts to fall. It falls down until it hits the ground. And we were able to break this up. The important thing was that the velocity calculated here after the accelerating phase, the rocket phase, is the final velocity here is the initial velocity there, and the same way here. The final velocity here, which is 0, is the initial velocity there. And the total distance going up must equal the total distance coming down. We used all that to work it out. So that's a long problem, but hopefully you got something out of it. Okay, so we are on problem number 54. So let's read it. It's on page 52. A parachutist with a camera descends in free fall at a speed of 10 meters per second. The parachutist releases the camera at an altitude of 50 meters. How long does it take for the camera to reach the ground? What is the velocity of the camera just before it hits the ground? So we have a parachutist, and he is moving at a velocity of 10 meters per second. So what's happened is that the parachutist slowed him down, and he's going 10 meters per second. He's not getting any faster. He's not going any slower. He's reached what we would call his terminal velocity. So the camera is also moving at the same speed as the parachutist. So let's put a little parachute here. Here's the guy. And in his hand, he's got a camera. And then he lets go of the camera. So what this means is that the initial velocity, V0, is something. Now, before we do that, though, let's define, usually I have to define positive, which is the positive direction. So I'm going to define positive as being up. We could just as easily do it downward. We just have to be consistent when we do this. So because this is pointing up, displacement is positive going up. Then, because the velocity is going down, it's going to be negative. So it's negative 10 meters per second. So a lot of these problems we've done, they just drop the ball, and that means it's 0 meters per second. So this is a way of giving you an initial velocity that's not 0. Okay, so when he drops it, now it's going to fall. It's going to speed up. we're going to assume that there's no drag on the camera, which is probably a pretty good assumption because it's a fairly small area for a higher mass. So the parachute thing, once he lets go of the camera, that's irrelevant. It just provides this initial velocity. Okay, so he releases the parachute at an altitude of 50 meters. So again, we're measuring displacement from the ground. So let me just make this a little bit longer. So from here's the ground. So his initial displacement is x, we'll call it x0, is equal to plus 50 meters. So usually we need to know three things to be able to use those equations, the simple equations that we have. Remember what they are that delta x, which is actually is x minus x0, it's the displacement minus the initial displacement, is equal to the average velocity times time. And then that's the first one. The second one says that v is equal to v0 plus a times t. We have that delta x. In this case, actually, well, we're just defining x as positive, which doesn't really matter. We can do that. Delta x is v0t plus 1/2 a t squared. And the final one is that v squared is equal to v0 squared plus 2a, a being the acceleration, times delta x. Okay, so we need to have three of these, no, three to get the other ones. So we know v0 is negative 10 meters per second. We know x is 50 meters, x0 is 50 meters, and x is 0 meters. So we'll define 0 meters here. X equals 0 here. X equals positive 50. That direction, okay. So delta, from these two, you get delta x is x minus x0, which is 0 minus 50, or it's negative 50. And that's because the change is going in the opposite direction that we've defined x to be positive. So that's negative 50 meters. Okay, what else do we know? Well, we know that acceleration due to gravity is 9.8 meters per second squared, but what's the sign? Well, this is positive, and we're accelerating in this direction, so it's going to be negative 9.8 meters per second squared. So now we do know three out of the 5, so we can find the other 2, which are the unknowns. How long does it take? And what is the velocity of the camera just before it hits the ground? So the question now is going to be, which one of these equations is the easiest one to use? So, and again, we could, we don't have to solve for the first one first or the second one second. We can choose whichever one it is. Let's just do it in the order I think that we have. So we want to know, part A is what is the time? So what equation, what do we know? We know V0, we know delta x, and we know A. So which one of these equations involves all that? Well, that one does. Now, I think that might be the only one. All the other ones have V in them, so that's not going to work. Well, let's see. Yeah, solve for time. So we could, it would involve a quadratic equation, which if we can avoid that, we would do it. So at this point, we could do one of two things. We could take this equation, the third equation, and put it in the form of a quadratic equation. So you do that, and you can get 2 solutions. And you can solve, if you multiply by 2a, so multiply by 2a, you get t squared plus 2a v0t minus delta x times 2a is equal to 0. And then we plug the numbers in, t squared plus 2 times the acceleration, which is negative 9.8 meters per second squared, times v0, which is negative 10 meters per second, times t, And then we have minus delta x, which is negative 50 meters, times 2 times a, which is negative 9.8 meters per second squared. And that'll equal 0, and we can get two solutions from that. So that equals 0. So if we multiply that out, we get t squared, and let's just multiply the numbers in front of the t in the second term. So we have 2, the negatives cancel out, so we have 2 times 9.8 times 10. So it's going to be plus 196t. And we have minus times minus times minus, so it's going to end up being plus. So we have 50 times 2 times 9.8. We get 980 plus 980 is equal to 0. In this case, the easiest thing you probably do is use the quadratic formula, which is minus b plus or minus the square root of b squared minus 4ac, all divided by 2 times a, which is 1. So we get negative 196 plus or minus. So let's see what we get inside. 196 squared minus 4 times 980 is, so we get the square root of 34,496 over 2. And we just take the positive square root, because if we had negative, we'd end up with a negative time, which we can't have. So there's only one positive solution. So we take the square root of 34,496. So you get 196. Interesting. Because I'm getting plus 185 here, which still gives me a negative number, which isn't going to work. So obviously I've done something wrong, which we can all make those mistakes. So what I'm going to do is I'm just going to pause for a second to find it, and then I'll let you know what it is. Okay, so I figured it out. Next time you have 2 errors. The reason I didn't start all over again, I just wanted to give you an idea of, how sometimes you can find out or realize you did something wrong. In that case, I realized I did something wrong when I got to the point where I had a negative time. You make mistakes sometimes, and you don't always know, but sometimes you can make these assumptions. So I keep doing that. I'm trying to put that little screen in. So let me explain what happened here. So this was correct, and what I should have done here was multiply by 2 divided by a, not 2a. So doing that, the a's would cancel out here, and the 2's would cancel out, and you get 1 for the coefficient. So you get t squared plus 2v0 over a t minus 2 delta x over a is equal to 0. So this is a quadratic equation. And then you use and then I plug the numbers in. So v0 is negative 10 meters per second. A was negative 9.8 meters per second squared. You have negative 2 delta x, which is negative 50 meters, and you have negative 9.8 meters per second squared for the acceleration. Okay, and then you use the quadratic, well, you plug them in, and then you get this quadratic equation. And then you plug it into the quadratic formula, which says that the time is negative b plus or minus the square root of b squared minus 4ac. So there's a minus sign there and a minus sign there. So the minus sign times the minus sign is positive. So you get 2.04 squared plus about 40.8. And so the square root of this whole thing is 6.705. Probably shouldn't have carried that many significant figures. 6.70. And you take the positive, because if you do negative, you get negative plus a negative, which is negative. It's plus, not multiplied. So negative minus something is a negative. So you take the positive part. So plus 6.7 minus 2.04 divided by 2 gives you 2.33 seconds, which is the answer. Okay, so that was the hard way, and I'm actually going to do it the other way now because I looked at the answer when I did this just to make sure where I went wrong. And what I did is actually solve for part B first. So this is the one you should be able to use. So v squared is equal to v0, which is negative 10 meters per second, quantity squared, plus 2 times negative 9.8 meters per second, squared times delta x, which is negative 50 meters. So you get 100, positive 100, because you square a negative, meters squared per second squared. And the second term is going to be 2 times negative 9.8 times negative 50, which is 980. So that's going to be plus 980 meters squared per second squared. And we add those two together, and we get 1080 meters squared per second squared. 980 plus 100 is 1080. Okay, then you take the square root, and we get plus or minus the square root of 1080, which is square root of 1080 is 32.9. And we take the square root of the units, which will give us meters per second. Now we have plus or minus, but from the physics of the situation, we know that the v has to be negative because it's falling down. So we only take the positive part, the negative part, because we know it's falling, going opposite the direction that we define positive. So it's negative 32.9. So we didn't have to solve any quadratic equation there. And therefore, now that we know 4 out of the 5, then we can use any of these equations to solve for t. And usually the easiest one is this one right here. So if you take v is equal to v0 plus at, that's the same as v minus v0 is equal to at by subtracting v0 from both sides. If you divide by the acceleration, you find out that t is v minus v0 over a. Because we know all that stuff. So v is negative 32.9 meters per second, and we subtract v0, which is negative 10 meters per second. And then we divide by a, which is negative 9.8 meters per second squared. The numerator is going to be negative 32.9 plus 10, which is 22.9 meters per second, divided by, so that's negative 9.8 meters per second squared. So from a unit standpoint, the meters cancel out, and the second cancels out with 1, and the remaining second, because it's in the denominator here, becomes the numerator. And so we get t is equal to 22.9 divided by 9.8. 2.33. So you get 2.33 seconds, which compares with doing it the other way, the harder way, 2.33 seconds. So you can see we get the same answer. In this case, we solve for velocity first and then calculated time. Here we calculated time, and with time you can calculate velocity because v is equal to v0 plus at. So the velocity is v0, which is negative 10 meters per second, plus a, which is negative 9.8 meters per second squared, times the time, which is 2.33 seconds. This seconds cancels out with that, so we end up with just meters per second. So we get negative 10 minus 9.8 times 2.33, and we get the velocity is negative 32.8 meters per second, which should match up with what we calculated up here. We're just off 1/10, but that's close enough. So see, there's two ways. And sometimes it's easier to solve part B and then solve part A instead of solve A and B. Sometimes I just have to look at it sometimes and figure it out. Okay, so we're doing problem number 56. And this is one of these problems that relates to velocity, acceleration, stuff like that. It's not a free fall problem because it's a speedboat. We're not dropping the speedboat from any place. It's moving along someplace. So what we have is we have a speedboat. So here's our lake. And here's our boat. And it's moving at, moving at 30 meters per second. Here's the buoy for the no wake zone. So he's moving with an initial velocity of 30 meters per second. So V0 is 30 meters per second. So he hits that buoy. Well, he doesn't hit it, but he goes by the buoy. And, well, actually, no, I didn't read the problem correctly. Anyway, he's approaching it, and he wants to slow down. So here's the buoy. And we'll say X is 0 right here, and then we go to here, which is 100 meters. So this is 100 meters. So this would be X. X0 would be 0 meters, and X would be equal to 100 meters. Okay, the pilot slows the boat with the constant acceleration of negative 3.5 meters per second squared. So this is our positive x direction, so the acceleration is actually in this direction, A, because it's going the opposite direction. As the displacement is negative, and that's what we give you in the problem, negative 3.5 meters per second squared. So he cuts back the throttle, and due to the drag of the boat in the water, it slows down. How long does it take the boat to reach the buoy? What is the velocity of the boat when it reaches the buoy? So again, we've listed what we know. We know that delta x is plus 100 meters. We know that V0 is plus 30 meters per second because the velocity is in the same direction as displacement. We know the acceleration is negative 3.5 meters per second. So that's what we know. And we don't know the other two things. What we did things, time and velocity. Well, luckily, that's what they're asking for in this problem. So let's add another page. Write the equations down. See what was delta x is equal to v plus v0 divided by 2 times t. V is equal to v0 plus at. Delta x is equal to v0t plus 1/2 at squared, and v squared is equal to v0 squared plus 2a delta x. So those are the four equations. And this may be one of these cases where we want to actually solve for velocity first, because if you think about it, what do we know? Delta x, we know v0, and we know a. So we could use this one, but that would require us solving a quadratic equation, which we can do, but it's not necessarily what we want to do. So we're actually going to solve for v first, and this was the one that we used in the previous problem, so we're going to use in this problem. So v squared is equal to v0, 30 meters per second, 1v squared, plus 2 times a, which is negative 3.5 meters per second squared. And then, what's the last thing? Delta x, that's plus 100 meters. So that's going to be 900 meters squared per second squared. So we square the 30 to give us 900, and we square the meters per second. And I'm going to put a little decimal point here to make sure we realize that there are 3 significant figures. And then we have this negative stuff, which means, because it's going to slow us down, 2 times negative 3.5 times 100. So it's negative 700. We have meters per second squared times meters, so we get meters squared per second squared, which is good because we have to have the same units here to be able to add or subtract things. So 900 minus 700 is 200. And then we take the square root. Now, what would happen if this was negative enough, this term was negative enough so this whole thing became negative? Well, what would happen is that somewhere before this distance, it would stop. And because it's just drag on the boat, it would just stop. It wouldn't go backwards. It's not like somebody's pushing him. Pushing is due to the movement, the difference in speed between the water surface and the boat. But in this case, it's positive, so we're still moving. We take the square root, and so you get theoretically plus or minus 14.1 meters per second. So you take the square root of 200, you get plus or minus 14.4. You take the square root of meters squared per second squared. So you just get meters in seconds. It's going to be positive for the reasons we just talked about. So the actual answer is just the positive part, 14.1 meters per second. So that's the velocity. Now once you know the velocity, then you know you can use any one of these equations. So let's rewrite what we know. We know delta x equals 100 meters. V0 is 30 meters per second. V is equal to 14.4 meters per second. And the acceleration is negative 3.5 meters per second squared. That was what it was, 3.50. So which one? We're trying to solve for time. So again, this one's probably the easiest one. We just did it earlier. Time is equal to V minus V0 over A. So V is 14.4 minus V0, which is 30. Both of these have units of meters per second. We divide by negative 3.50 meters per second squared. This is going to be negative 14.4 minus 30. It's negative 15.3 divided by negative 3.5 gives us 4.46 seconds. And again, the seconds work out because these cancel out. This cancels out with one of those, and this is 1 over seconds, but it's being divided. So anyway, it comes out to be 4.46 seconds. So those are the two answers for the problem. I'm just going to do a quick check to make sure I did it right. And this is problem number 56. So let me just make sure I did it right. 14 point. I think it's 14.1. What did I get? 14.4. No, 14.1. I got it right. That's what I got. 14.1 and 4.53 seconds, which I think is 4.46. Oh, it's because I copied that wrong. It should have been 14.1. So if you get 14.1 minus 30 divided by negative 3.5, you get 4.54. So both of those correct. Okay, we're doing 63. Apparently I did 53. I don't know why. So you have 53 if you want to look at an extra problem. But 63, chapter 2. So we have a ball thrown upward from the ground with an initial speed of 25 meters per second. So let's draw some ground in here. So here's the ground. Just needs it to be slanted. And let's define positive y in this direction. Again, I don't know why I got tilted there, but it did. Okay, so there's positive y. It's thrown up from the ground, and let's say there's A is the one that's dropped from the ground, and B would be the one that's dropped. So what we can say is that V0A is positive 25 meters per second. And let's draw a building here so we can have that to look at. So here's the building. And the building is 15 meters high, so let's draw an arrow here just showing the height. So it's 15 meters. This is, of course, 0 meters. And we have, for both cases, that the acceleration is negative 9.8 meters per second squared. And what else do we know? Well, what we're looking for is the time when they're both at the same height. So let's write which equation would we use that involves time, acceleration, v0, and delta y. Well, it's the third equation, which says delta y is equal to v0 times t plus 1/2 a t squared. So the way we're going to work this to keep everything straight, so let me put 2 pages together here so we can look at this. So let's say delta y sub a is the final height minus the initial height, which was y0a, and that's equal to v0a t plus 1/2 a t squared. And we'll say delta y sub b, which is the dropped one, is y minus y0b, which is equal to v0b t plus 1/2 a t squared. And so what we want to do, we want to get to the point where we're at the same height. So if we solve each one of these for y is equal to y0a plus v0at plus 1/2 at squared, and y is equal to y0b plus v0bt plus 1/2 at squared. Okay, now we want the point where these two, y sub a, I guess we could call this y sub a and this y sub b, we want to where these are equal to each other. So we just set them equal to each other. So what we have is then y0a plus v0at plus 1/2 at squared, and then y0b plus, actually I got to set it equal to there. So we're going to set it equal to it. So that equals y0b plus v0bt plus 1/2 at squared. Well, you see these cancel out. They're on both sides. And what else do we know? Well, y0a is, well, that's A is the one that's thrown. So y0a is 0 meters. We know y0b is 15 meters. We know that v0a is positive 25 meters per second. And we know that v0b is 0 meters per second. So this simplifies things considerably. The only thing we don't know is t, which is what we're going to solve for. And once we know t, we can just plug back in and find the height. So let's do that. So plug it in. So you get 0 plus v0a, which is 25 meters per second, times t is equal to v0b, which is 15 meters, plus v0b, which is 0 meters per second, times t, that goes to 0. So the time is going to be equal to 15 meters divided by 25 meters per second, which is 0.6 seconds. So that's the time that they're going to be at the same height. Actually, that's what they're asking for, 0.6 seconds. So let's just pause for a moment. Okay, so that is the right answer, and that's pretty much the way they worked it in the solution manual. They didn't ask for it, but let's say what is V sub A and V sub B? Well, we can actually use another equation to do that instead of plugging in. So we had equation 2 says V is equal to V0 plus is equal to A times T. So the velocity of object A, which is the one that's thrown up, is V0, which is 25 meters per second, plus the acceleration, which is negative 9.8 meters per second squared times the time, which is 0.6 seconds. So when we multiply meters per second squared times meters, we get over seconds, we get meters per second, which is good because those are the right units. So we get 25 minus 9.8 times 0.6. So VA is 19.1 meters per second. And V sub B is going to be 0 meters per second, which is the initials. And then we have negative 9.8 meters per second squared times 0.6 seconds. So we have negative 9.8 times 0.6 is negative 5.9 meters per second. And they both make sense. So you start at 25, you've slowed down to 19, and this one is being dropped, so it starts at 0 and ends at this 5.9, which actually you see the difference is the same. 25 subtracted 19.1 is 5.9. It's not a coincidence. And if you wanted to calculate delta y, we could use any one of the equations almost, except for the one we just used here. And I just accidentally turned up my slate, so I'll have to get the thing back going again. So I'm going to use the first equation, which says you take the average velocity divided by 2. Well, take the average velocity multiplied by t. So delta y is going to be equal to okay, so sorry for the pause there. Somebody's coming to get my trash. So delta y, which for A is just y sub A, because y0 is 0, so we can use this one. So the velocity is equal to, or delta y is equal to 25 meters per second plus 19.1 meters per second divided by 2 times the time, which is 0.6 seconds, and you get that the height above the ground is 25 plus 19.1 divided by 2 times 0.6 seconds. It should be less than 15 meters, because if it isn't, then this couldn't have happened. And it's actually 13.2 meters. So the balls meet almost near the top. And that's because this is moving fast to start with, so it goes a lot further than does the one that's coming down, which starts from rest, and it takes a while for that thing to accelerate. So we know that, so this is also equal to y sub b. In the case of this, with object B, delta y is y minus y sub b 0, which is 15 meters. So that's why, in that case, you'd have V would be 0. Actually, V0 is 0. So we'd have V, which is negative 5.9 meters per second, plus V0, which is 0, divided by 2 times 0.6. So you get negative 5.9 times 0.6 divided by 2, which is negative 1.8 meters. But since y sub b0 is 15, you'd get y is equal to y sub b0 minus 1.8 meters. So y is equal to 15 minus 1.8 meters, which is 13.2 meters, which is the same answer we got up here. So all this will work out as long as you're very consistent about how you set up your system and where you measure things from. This is our last problem, and this is also a blue problem, so it's going to be not easy, but it's I don't think it's quite as hard as number 53. So let's read the problem. 2 students are on a balcony 19.6 meters above the street. One student throws a ball vertically downward at 14.7 meters per second. At the same instant, the other student throws a ball vertically upward at the same speed. The second ball just misses the balcony on the way down. What is the difference in the 2 balls' time in the air? What is the velocity of each ball as it strikes the ground? How far apart are the balls 0.6 seconds after they are thrown? So let's draw a picture. So let's make a building. And so here's the balcony. So what's going to happen is let's define the ground at y equals 0. Define positive y going up. And so y0 here, the initial height, y0 is equal to 19.6 meters. And there are 2 cases. I'll probably use different colors again. So we're going to have one person throwing it up with an initial velocity of 14.7 meters per second. We're going to have the other person throwing it down with a V0, and it's going to be negative 14.7 meters per second. And ultimately, the delta y, in both cases, is going to be negative 19.6 meters because the delta is going in this direction, which is negative. It's going down, whereas the positive y is going up. So either case, so let's look at, before we do that, we'll do these on separate pages, but what do we know? We know acceleration for both cases. So the things that are common, we'll use black, at least to define the negative 9.8 meters per second squared. We know that delta y is negative 19.6 meters. And the 2 things that are different are the V0. And our equations, which are also common, is that delta y is equal to v plus v0 over 2 times t. V is equal to v0 plus at. Delta y is equal to v0t plus 1/2 at squared. And v squared is equal to v0 squared plus 2a delta y. So those are the 4 equations. So let's add a page. We're going to try to do these on the same page. So one problem. V0 equals positive 14.7 meters per second. A is equal to negative 9.8 meters per second squared. And delta y is equal to negative 19.6 meters. The second case is V0 equals negative 14.7 meters per second. A is equal to negative 9.8 meters per second squared, and delta y is equal to negative 19.6 meters. So, what are we looking for here? Read the problem again. What is the difference in 2 balls of time in the air. So let's calculate the time. Possibly, this is the one we would calculate time directly, but that one's going to that's going to solve the quadratic equation, so we're going to avoid that. So the only other thing we don't know is what is V. And so which ones involve V? Here's delta Y, A, V0. Now the thing is that when you take this, you square these kind of lose their initial direction. And so, but, yeah, okay. Just thinking this through here. But we are going to use this one. V squared is equal to V0 squared, which is, in this case, positive 14.7 meters per second squared, plus 2A, negative 9.8 meters per second times delta Y, which is negative 19.6 meters. So let's plug those in there, 14.7 squared plus 2 times 9.8 times 19.6. The reason I didn't say negatives because those cancel out. So you get 600 approximately. V squared, that's meters squared per second squared. So V is the square root of that, which is 24.5. Now it's plus or minus because we took the square root, but we know that if this thing goes up and then comes back down again, it's going to be going negative when it hits. So in this case, it's negative 24.5 meters per second. Well, if you look at the red part, the only difference is that you have a negative sign here, but when I square it, it's going to be the same. So I'm just going to say plus the same thing. So what we end up with is V squared is equal to 600 meters squared per second squared, where V is equal to plus or minus 24.5 meters per second, and we're going to take the negative because it's falling, negative 24.5 meters per second. Okay, let me just check my solution here. Make sure I'm doing this correctly. Notice the use of adverb, correctly. Okay, so that's correct. I did it correctly. Okay. Pet peeve, even though I'm not an English major, is the use of adverbs. Okay, so they're both negative 24.5. So what's going on here? Well, what happens is when this thing goes up, it'll go to a maximum height to go to 0. When it falls, and when it gets to this point, it will now be falling at the same velocity it was going up. So it goes up at 14.7, goes to 0, comes back down. It's now negative 14.7, which is exactly what it was if I threw it down initially. And so from this point onward, the blue one behaves just like the red one. They both hit the ground at the same speed. So you have this kind of symmetry with free fall. If you throw something up, when it comes back down to the same height, you can have the same velocity. And this is assuming there's no air drag. Okay, so what is the difference in two balls? Okay, what is the velocity of the ball? Each ball as it strikes the ground. Well, that was the answer for part B. Now that we know that, we can then use this equation to find the time. So in this case, we have solve for time, V minus V0 over A. So the time is equal to, V is negative 24.5 meters per second. We subtract the V0, which is positive 14.7 meters per second, and we divide by the acceleration, which is negative 9.8 meters per second squared. And it's going to come out positive because we have negative in both the numerator and the denominator. So we have negative 24.5 minus 14.7. And I made a mistake there. Negative 24.5 minus 14.7 divided by negative 9.8, and I get 4. seconds, 4.0 seconds. Now you know why they chose that number right there. And then for the red one that I throw down, of course, it's going to take less time. V is still equal to negative 24.5 meters per second, but V0 is negative. And I divide by negative 9.8 meters per second squared. So the numerator is still negative, but it's less negative. So we have 24.5 plus negative 24.5 plus 14.7 divided by 9.8, negative 9.8, which will give us positive 1. So this is 1 second. So this one goes up, it actually goes up 1.5 seconds, down 1.5 seconds. That's for a total 3 seconds, and then it takes another second to drop. So the answer to part A, what is the difference in two balls' time in the air, is 3 seconds. So say delta T is 4 seconds minus 1 second, which is equal to 3 seconds. The blue ball stays up 3 seconds longer than the red ball. And then it says, this is really a separate question. How far apart are the balls at 0.6 seconds after they are thrown? So let's add a page in here. So in this case, time, let's use the same colors again. So for this part of the question, V0 is still 14.7 meters per second. A is still negative 9.8 meters per second squared, and the time is equal to 0.8 seconds. For the red ball, V0 is negative 14.7 meters per second. A is negative 9.8 meters per second squared. T is the same. So what we're going to do is we're going to calculate delta Y in both of these cases. So what are we given? We're given, just a second here. Yeah. Okay, sorry for the little break there. I had a student looking for somebody who said that they were in my room, but they're not because it's me. Okay, so what we're saying was we want to find out, what were we trying to find out? How far apart are the balls? So this one has B0, T, and A, so we can just plug directly in this one. So delta Y is going to be V0, which is 14.7 meters per second times time, which is 0.8 seconds, plus 1/2 A, which is negative 9.8 meters per second squared, times T, which is 0.8 seconds squared. And if you calculate that, it should be going up. It should have a positive delta Y, I think. Because I don't think it has time to slow down. I know it doesn't because it doesn't have time to stop because it took 1.5 seconds to stop. So we have 14.7 times 0.8 plus 0.5 times negative 9.8 times 0.8 squared is 8.6. So positive 8.6 meters. If we do delta Y in the red, we have negative 14.7 meters per second, 0.8 seconds, plus 1/2 A T squared. So it's the same equation, but I'm going to change it to negative 14.7. And I get negative 14.9. So if we add those two together, the total delta Y is going to be the sum of those two. And actually, it's not going to be, so it's going to be the difference of the two. So we're going to take, we'll take blue delta Y and subtract red delta Y. And so if we plug those in, we get 8.6 meters going up. Then we subtract a negative number, so 14.9 meters. And so we get 8.6 basically plus 14.9, which is 23.5 meters. So that'll be the distance between them. This one's going up, this one's going down. And so we add those two together, and that would be how far they are apart after 0.8 seconds. Now, in 1 second, this thing would have hit the ground, because we calculated that earlier. So it's just probably about here. And again, let me just check the solution. So what was it? Worked. 23.5.